Hello students, I am S.K. Nigam, PGT Chemistry, Kendra Vidyalaya. So in this lecture, I am going to discuss some rest of the topic of chapter 1, and the first one is the electrical properties of the solid, and next one is the magnetic properties. So in this lecture, in this section, we will discuss only two topics, electrical properties and the magnetic properties. Clear? So electrical properties. Electrical properties are basically we are considering three kind of the materials on the basis of electrical conductivity. They are conductors, insulators, and the next one is semiconductor. So conductors, how can you categorize which kind of solid is conductor, which is insulator, and which is semiconductor? So conductors, on the basis of the value, the conductivity value, it ranges from 10 to the power minus 20 to 10 power 7 per ohm per meter. This is the range of the conductivity. So on the basis of this, the conductors are those solids whose conductivity ranges from 10 to the power 4 to 10 to the power 7 per ohm per meter. They are known as conductors, and metals are very good conductors. They have 10 to the power 7 per ohm per meter of range. The next one is insulator. Insulator whose conductivity ranges from 10 to the power minus 20 to 10 to the power minus 10 per ohm per meter. So they are insulators. And what are semiconductors whose conductivity ranges from 10 to the power minus 6 to 10 to the power 4 per ohm per meter. And it is also mentioned in my notes also. So this is all about the kind of solids on the basis of electrical conductivity. Clear? Now next one is conduction of electricity. How in the case of metals electricity is conducting? So for conductivity there are basically two points, either free ions are there or free electrons are there. So in the case of metals, free electrons are there which are responsible for the conductivity. So if electrons are moving freely, then you can say the metals are conductor. So in the case of solid state or in the case of liquid state, in both the state the metals are showing the conductivity. So how you may define that the metals are a good conductors? So I am going to just describe it with the help of this diagram. So basically the detail of this band structure will be in your physics lecture, but here there are certain easy things are there which we are going to consider here. So in the case of metal or in the case of any element, there are two bands, the valence band and the conduction band. So valence band are basically these kind of the bands where electrons are normally found, and conduction band is that orbital, that molecular orbital or the atomic orbital where electrons can move very freely. So if conduction band is near to the valence band, the electrons can easily jump from valence band to the conduction band, and there is the conductivity, that element or that substance can show conductivity. So in the case of metals, there are two possibilities. The first possibility is this is the first possibility. In this possibility, for example, in this possibility, first group elements are considered, where the general electronic configuration of outermost shell is ns1, means there are the vacancy of one electron. So in this case, the orbital, the valence band itself is acting as conduction band, because the place where electron is present originally, it is the valence band, and the other position is the conduction band. And for example, in second group element, the electronic configuration is ns2. So ns2, the s subshell is completely filled, but np orbital is having not very much difference of the energy with the ns. So in this case, the ns orbital is the valence band, and the next unoccupied orbital is considered as the conduction band. And in this case, the conduction band and valence band is overlapping with each other up to some extent only, not the complete overlapping is there. Up to some extent they are overlapping on each other. So in these two conditions, metals, in the metals, it means that electrons can easily jump from valence cell to where conduction band easily. In this case, or as well as in overlapping bands also. In both the cases, electrons can jump from one place to the another place, and the conductivity will be shown. Clear? So all this kind of the concept is written in this paragraph, clearly mentioned here. So metals are a very good conductor on the basis of that concept which I have explained you. Now when we are talking about the conduction of electricity in the semiconductor, then what is happening? So again in this diagram, first of all, in the case of insulator, the gap between this valence band and conduction band, which is termed as forbidden zone or forbidden energy gap, this is very high. So electron cannot jump from valence band to the conduction band, and it cannot conduct electricity. Clear? So this is insulator, because electron cannot jump from valence band to the conduction band. And in the case of semiconductor, there is a gap, but this gap is not very high. The energy difference is not very high. Therefore, electron easily jump from valence band to the conduction band, and semiconductor can conduct electricity easily. Clear? So all this is mentioned in this paragraph. Somewhere it is written. In case semiconductors, the gap between the valence band and the conduction band is small. Therefore, some electrons may jump to the conduction band and show conductivity. Clear? And the electrical conductivity of semiconductor increases with rise in temperature, because electrons will get more energy and they will jump from valence band to the conduction band easily. So the basic examples are silicon and germanium, because they are the 14 group element and they are termed as intrinsic semiconductor. So intrinsic semiconductors are only the silicon and germanium, or you can say 14 group elements, but the conductivity is not very high, and you may increase the conductivity of these two kind of elements, silicon and germanium, means, or you can say intrinsic semiconductors can be increased with the help of introducing some kind of impurity, and this process of adding impurity is termed as doping. So their conductivity is increased by adding an appropriate amount of suitable impurity, which is, this process is termed as, what is the name of the process? The name of the process is doping. It is again 1 mark question. What is doping? Doping is the just addition of the impurity for enhancing the conductivity of the semiconductors. So this is the doping, and doping is of because it is of two type. When you are adding electron rich impurity, then another kind of semiconductors are prepared, and when you are adding the electron deficient impurity, then another kind of semiconductors are formed. So two kind of semiconductors are prepared here: electron rich because of adding of electron rich impurity and electron deficient impurity. What is happening? So in this diagram you may very clearly just observe. So this A diagram is of pure silicon atom, perfect crystal, where 14 group element. It means the tetravalency is there, and all the elements, for example, if you are considering this element, so 1 2 3 4 electrons are of this particular silicon, and 4 other electrons from the other silicon atom. And if you are adding an electron rich impurity, for example, 15 group element is added here as impurity, for example arsenic is 15 group element. So what is the difference of this 15 group element and the 14 group element? 15 group element is having 5 electron in the valence shell, and 14 group is having 4 electron in the outermost shell. So out of 5, 4 electrons are just reacting with, or you may say they get attached with the nearby silicon atoms, and one electron become free. So this free electron become the carrier of the current, and when you are just passing current through the semiconductor, this electron is carrying the current for jumping from one position to another and another, like this. So because the carrier in this case is electron, that's why it is termed as n-type semiconductor. So when this n-type semiconductor is formed, when the impurity is of 15 group element. And the next one is p-type semiconductor. Here P is for positive. When this type of semiconductor is formed, when you are doping with the help of 13 group element as a impurity. For example, boron is 13 group element, and it is having 3 electrons in the outermost shell. So out of 3, all the 3 are just accommodated in the nearby silicon atom with this covalent bond, and one position become free. Here one position is free, which is because of the lack of one electron, which is not having in the case of boron. So this may be considered as positive hole. This is considered as positive hole where no electrons are there. And now if you are passing current through this semiconductor, then what is happening? The electron which is present to the nearby silicon, the electron jump from here to this position, means the vacant position means the whole position of this boron may be filled by the electron which is jumped from the nearby element, but from where this electron jump, here the hole will be appear. So it seems when you are passing current, the holes are moving, that's why, and holes are considered as positive holes, that's why they are termed as p type semiconductor. Clear? So if you are doping, so two kind of the impurities are there: electron rich impurity, which is the 15 group element, and electron deficient impurity, which is 13 group element. If you are adding electron rich impurity, means 15 group element as impurity, then the electrons are the carrier, that's why they are n type semiconductor. And if you are adding 13 group element as impurity, then it is just deficient, it is lacking one electron, that's why the positive holes are the carrier and they are considered as p type semiconductors. And it is also mentioned in my notes, also. Clear? So in my notes also all these points are here: n type semiconductor, p type semiconductor, with the diagram also it is representing here. Now application of n type and p type semiconductors, where they are used. So there are various uses. Where are the application? First of all, they are used as diode when one n type and one p type semiconductors are mixed with each other, then they form diode. And the diode is used in rectifier. What are rectifier? Rectifier are the devices which are using to convert AC into DC and DC into AC, alternating current to direct current and direct current into alternating current. One another way where it is just sandwiched between two different kind of the semiconductor. For example, NPN, NPN or PNP. These two kind of the they are termed as transistor, in which in this kind P is sandwiched between N, and in this kind N is sandwiched between P semiconductor. So they are the transistor. And basically transistor are used in the case where you have to amplify the signals, means audio to electrical and electrical to the audio signals. Their transistors are used. And photovoltaic cells, they are also having diode which is used to convert sunlight energy into the electrical energy. Along with this germanium and silicon, there are various other kind of the semiconductor, because the basic concept behind the semiconductivity of germanium and silicon is the tetravalency. So keeping in mind the tetravalency, there are large variety of solid state material which have been prepared by combination of group 13 and 15 or 12 and 16 to simulate average balance of the 4 as in germanium and silicon. For example, one 13 group element and one 15 group element. So electrons in the case of 13 group is 3 and electrons in the case of 15 group is 5. So 5 plus 3 is total is number is 8. So you can consider it, they are following the tetravalency. So the examples are indium and strontium, then aluminum and phosphorus, then gallium and arsenic. And gallium, arsenoid, they are a very fast responsive semiconductor. It revolutionized the electronic industry when it came into existence. Some more examples of the 12 and 16 group: ZNS, CDS, CDSC and HGTE, they are the examples. And it is also 1 mark question in the board examination. Write a short note on 12-16 compound or 13-15 compounds. So nothing very difficult in this heading. You may only write that in 13-15 group element, one element is from 13 group and one element is from 15th group, and they are collectively they are forming tetravalency, and they can be used in the place of semiconductor like this. One more interesting thing is there: some metal oxides show remarkable property in the electrical conductivity. For example, TiO, CrO2, ReO3, they behave like metals. And some rhenium oxides, they are metal, they have the conductivity of copper and the appearance too. Certain metal oxides of vanadium, they show metallic or insulating property depending on temperature. On increasing or decreasing temperature, they can show both the kind of the property. Clear? So it is also in my notes also. Now the next heading is magnetic property. It is the last heading of this chapter, magnetic property. So Why this magnetic property is there in the solid? It is because of the electrons. So electrons are having two kind of the motion. They have the orbital motion around the nucleus and spin around the own axis. For example, as our earth is having the revolution around the sun and rotation around its own axis, similarly electron is also revolving around the nucleus and rotating around its own axis. So because of these two kind of the motion, these electrons are having magnetic moment. Even this magnetic moment is very small, it is not very high, but they, because of these two kind of the motion, they have the magnetic moment. And this magnetic moment is calculated in the unit which is termed as Bohr magneton. Mu b with this notation it is representing, and it is equal to 9.27 into 10 power minus 24 ampere meter square. So this is the reason behind the magnetic property of the element. So if any charged particle is revolving around any center, it is experiencing a kind of magnetic property. Clear? So on the basis of the magnetic properties, solid substances are classified into 5 categories. They are paramagnetic, diamagnetic, ferro, antiferro and ferrimagnetic material. So first is paramagnetic material, paramagnetism. So paramagnetic, what are paramagnetic materials? They are weakly attracted when you are placing this in the external magnetic field. So why they are weakly attracted? Because there are free electrons, and these free electrons have some magnetic moment and they align themselves in the same direction from of the external magnetic field. So because of this, they are weakly attracted towards the external magnetic field. So the what is the reason behind? Because they are having one or more unpaired electrons. Clear? So these are the paramagnetic substances. Now next one is the diamagnetism. Diamagnetism, they are the substances which are weakly repelled by the external magnetic field. For example, H2O, NaCl, C6S6. So these are the examples. Why they are just weakly repelled? Because they don't have any kind of magnetic property, because in this kind of material they have all the paired electrons, there are no unpaired electrons. So if all the electrons are paired, so magnetic moment of one electron is cancelled by the magnetic moment of another electron, because the spin of both the electrons are opposite to each other. So they are diamagnetic material. The next one is ferromagnetism. Ferromagnetism, this is in the case of iron, cobalt, nickel, gadolinium and CrO2. So they are strongly attracted towards the external magnetic field. If you are applying the external magnetic field and the substance is strongly attracted towards it, then you may consider these substances as the ferromagnetic substances. So along with this, it is also a kind of permanent magnet. They form permanent magnet. Why they form permanent magnet? Before it, you have to just study about the domains. So basically the metal ions in the case of ferromagnetic substances, they collectively termed as domains, and these domains are acting as a tiny magnets. So when you are not placing this material in the external magnetic field, all these tiny magnets are unmagnetized, and as you place this ferromagnetic substance in the external field, then what is happening? It is in this diagram, all the domains align themselves in a same alignment along the direction of the external magnetic field, and they get extremely magnetized. That's why they will strongly attract towards the external magnetic field, and after removing the external magnetic field, they remain in such position. That's why they form the permanent magnet, and they are very strong magnet also. Clear? Now next one is the antiferromagnetism. Antiferromagnetism, these are the substances which are strongly repelled when they are placed in the external magnetic field. And why they are strongly repelled? Because the arrangement of the domains are alternate, parallel, antiparallel, parallel, antiparallel, parallel, antiparallel. It means the magnetic moment of one domain is cancelled by the magnetic moment of another domain. Clear? Now next is the last is the ferrimagnetism. Ferrimagnetism is the behavior, or you can say they are the substances which are weakly attracted towards the external magnetic field, because in the ferrimagnetism there is the unequal number of parallel and anti-parallel arrangement of the domains. Because of this, there is not exact very much high value of the magnetic moment. That's why they are weakly attracted towards the external magnetic field, and the examples are Fe3O4 or ferrites like this. So these are certain examples. These substances also lose ferrimagnetism on heating and become paramagnetic. So these all are the 5 kind of the magnetic materials, and it is also mentioned in my notes. It is clearly mentioned, all the points are written here, so you may go through this notes. Clear? So this is all about the chapter, the discussion, or you may say the theory portion of this chapter. One more lecture will be there in which I will discuss the in-text question, the examples, and the exercise. Thank you.